This chapter we're going to be focusing on cognitive views of learning. And this chapter has a lot of information, so I'm only going to be covering some of the chapter highlights, but be sure to revisit those sections in which are not covered in this particular PowerPoint. Behaviorism was concerned with investigating the observables. If you could see it, then it could be measured. And cognitive psychology really came about as a reaction almost to behaviorism, and that while behaviorists focused on those observables, cognitive psychologists said, there are things that we can't directly view, but they're still important to study. And cognitive psychology largely got its start through a computer metaphor, the way that people were thinking about our internal thought processes. So they said, yes, you can study how people think, even though, again, we couldn't directly observe, for example, how someone thinks, or maybe we might not even agree upon sometimes how people are thinking, at least the theory behind it. But with this computer metaphor, Neisser has said it was because the activities of the computer itself seem in some ways akin to cognitive processes. Computers accept information, they manipulate symbols, store items in memory, and retrieve them again, classify inputs, recognize patterns, and so on. So this gave us a way to actually be talking about how we process information by using the computer analogy. With this analogy, we can think of the brain as hardware, and your book talks about the brain and cognitive learning. There's a whole branch of science with cognitive neuroscience that talks about what parts of the brain are associated with specific activities. For example, if I'm giving someone a planning task, we're going to see different areas within the frontal lobe being activated. If I'm giving someone a task in which they're having to bind together new pieces of information, the medial temporal lobe within the temporal lobe will be activated. And basically what you can do is you can start saying, these areas are associated with specific processing. And as a cognitive psychologist, when you're focused on, instead of looking at brain activity, we're focused on what are those internal processes that are ongoing, that is producing that behavior. And so cognitive psychologists study the software. Whereas behaviorism, the smallest unit was a reflex, cognitive psychologists, what we study are representations. And we can look at it in terms of we have a piece of information, it gets processed, then we have more information that gets processed, and so forth. We're largely going to be focusing on memory, and really when we talk about learning and memory, they're two sides of the same coin. But memory is the means by which we retain and draw on our past experiences to use this information in the present. There are three components of memory. There's the encoding, which is putting information into memory. Think about it in terms of a Word document. As you are typing in those letters and the words, you're putting information into that Word document. So you're putting information into the Word document would be, let's think of it as memory. Storage, whenever we store that information in memory. So think about in a Word document hitting the Save button. And then we, for example, close out the document and we want to return to it later. That would be an example of retrieval. So getting that information out of memory. So when we talk about memory, we talk about encoding, storage, and retrieval. And your book presents a model of the information processing approach, including memory and knowledge. And we're going to be talking about some of these key elements of this model, and we'll be going back and forth to these different units. The main idea here, though, is just as a preview, what happens is there's lots of information out there in the environment. So you have stimuli, and these take the form of different sensations. So you'll have sights and sounds and all sorts of stimuli out there. And what you are attending to gets into sensory memory, so the things that you notice. And what you do is the things that you are attending to, you perceive them as certain sights, certain sounds. So the perception is your interpretation of these sensations. Whenever you're thinking about these things, you can think about this as in working memory. Working memory are those things you're currently attending to. This is your workbench. So this is the information that you're currently working with. So think about it as a workbench. Whenever you are doing a task, you'll want to have those tools on your workbench. And so working memory, again, is what you're currently processing. And what you can do is whenever something's in working memory, you're trying to learn it, you're trying to save it, and put it into your long-term memory so that later on you can reactivate or retrieve that information. When that happens, then it goes back into working memory, because working memory are the things that you're currently thinking about. So again, information or memory from the past can be put back on that workbench whenever you're thinking about it. And this can direct your attention to thinking about other things in your environment that are relevant to whatever that information is that you were thinking about. Okay, so now we've talked about that flow from sensory memory to working memory to long-term memory, and how this can go back and specifically think about retrieving it and thinking about it on your workbench again. We're also going to be talking about how knowledge influences your perceptions. Think about it in this way. You have in long-term memory different memories, and these memories can act to influence how you perceive the world. For example, if I have a schema for how something works, then whenever I come into contact with new information in my environment, I might interpret it differently based on what's in my long-term memory. This sometimes could be particularly difficult whenever you're trying to get people to not be biased. Sometimes their past memory will make them biased and they'll interpret things differently. So for example, if you have a scenario of a story with thinking about a student who gave you a lot of problems, and say that student was named Jason and he was just a terror. Well, then next time you have a student in your class whose name is Jason and he's starting to show some signs of behavioral disruptions, you might actually then start to look at that and start interpreting his behavior based on your negative impressions from a previous episode with a previous student. And so sometimes long-term memory, your knowledge, can influence how you perceive things. Now, that's a negative example. There's also examples where we have long-term memory where we bring up a past event, and that knowledge can guide us and help us interpret information in our environment. There's also a link from sensory memory to long-term memory going the opposite direction. If you look at sensory memory to long-term memory, there's implicit memories. And these memories are memories that you have that you don't really have an association for even learning it. And we'll talk more about implicit memories in a subsequent slide. And finally, the outermost circle is executive control. And this deals with coordinating, organizing information. And you can see how this would be something that encompasses this whole information processing scheme. Let's begin with looking at sensory memory. This is the initial processing from the 5 senses, such as sight, sounds, and smells, etc. And what we have is we have all this stimuli in the environment. And what we do is we take these senses, and some of them that is, and we put them into a sensory information store so that we can process them. Now the store has a large capacity. It can hold up to 20 items. And we know this from a classic experiment by Sperling. And what Sperling did was he flashed up very, very quickly a series of digits and letters in an array of 4 items per row in 3 rows. And I have an example here with just X's. And so what he would do is he would flash that up, and here we have 12 items, and we'd ask the participants to recall as many of those items that they could. And it was very, very quickly, and people on average recalled 3 or 4 items. But here's the thing. They said they felt like they knew there was more, but they couldn't recall it. So what Sperling did was something known as a partial report. So he would show them all of those 12 items in a single presentation, but then immediately after the presentation, he would somehow cue them to which row they should recall. So again, the initial presentation, they're seeing all 12 items. They have no idea which row he's going to ask them to recall, but that cue is presented afterwards. And what he found was, on average, people recalled 3 or 4 items, suggesting that they actually were getting all of that information in. But what happened was, as they were recalling it, the other information that they had was quickly decaying. And we'll talk about decay a little bit later, but in terms of sensory memory, it seems that they were getting that information in, but they couldn't report it quickly enough. So again, sensory store actually is large capacity. But as I was saying before about this temporal component, it seems to be very short. So if you're not currently thinking about it and you don't get it into the next store, it rapidly disappears. Again, there's lots of sensory information in the environment, but perception is whenever we detect that information and we assign meaning to it. Your book also talks about Gestalt theory. And Gestalt theory was very popular as a psychology camp, and we still think about it today as being something that's important as well. But with Gestalt, they talk about how people look at the whole. So it's not that people are just looking at the individual pieces, but instead you organize these units into a whole. And the way that we perceive the world can be influenced by how we're processing the information. Are we looking in terms of a bottom-up approach or a top-down approach? With the bottom-up approach, this one is the one that the book talks about when they talk about Gestalt principles. But this one is whenever you analyze features of a stimulus, so you attempt to put pieces of a whole together to make sense of them. There's also top-down processing, and that's interpreting stimuli based on expectations. This one here, with top-down processing, I always think of this is how proofreading mistakes happen oftentimes. Whenever top-down processing, whenever you're reading through a paragraph you've written, you think that this word should be there, and you think you've written it, so whenever you're proofreading, sometimes you don't realize that you've left out a word, particularly with articles. Sometimes we'll leave out an A or an but what it happens is our mind fills it in. So this is an example of top-down processing. We interpret and we see what we think is there because we have the expectation that it would be there. So we can contrast top-down and bottom-up processing. With bottom-up processing, the stimuli is guiding our interpretation or our expectations, whereas top-down, our expectations are guiding what we're seeing. And I'd like for you to think about how these scenarios would play out in terms of our expectations for our students then. I've kept saying there are tons of stimuli out there in the world. There are all these potential sights and sounds and so forth in our environment, but there are only certain things we attend to, and attention is selective in that way. But it also is limited in that we don't seem to have an unlimited pool. There are various theories that talk about just how much attention do we have available to devote to attending to different things in our environment. One thing that we talk about as teachers and what we want to have become this way is automaticity. We know that attention you don't have an endless supply of it, but automaticity frees up some of these resources. Automaticity is processes that initially require much attention and eventually become automatic, and you're on autopilot. Whenever we're driving home, you're probably oftentimes on autopilot because that route is so familiar. Another example is reading. Whenever you have a student who has had so much practice reading, over time it eventually becomes automatic. So now I'm not sounding out every single word and thinking about the letter, I'm doing it automatically. And so much so that reading is automatic that we can fill in the gaps even whenever particular words are missing. And here I give you an example of just how automatic reading is, and that even whenever the words are scrambled, we still are such good processors that we can figure out what these words are because reading has become that automatic for us. We'll also talk about working memory, and this is the workbench or the information that the brain is working on currently at the moment, and includes both temporary storage and active processing. Badly working memory model is the one that people refer to, and this is comprised of the central executive and 3 systems that interact with long-term memory store. The phonological loop is fundamental in that you can encode some sort of auditory stimuli or even verbal stimuli and put it into an acoustical or verbal code. And it's comprised of a phonological store that stores approximately 2 seconds worth of auditory information. It's not a certain number of items, but instead is a certain duration. Within the phonological loop, you have subvocal rehearsal, and this is a process for maintenance. So for example, saying to yourself over and over again a phone number that someone just gave you would be an example of having something in the phonological loop. We also have the visuospatial sketchpad, and here's where we store visual and spatial info, similar to imagery. And then we have this episodic buffer, and this is one that Badley proposed a little bit later on. Originally it was just the 2 systems, but he proposed this 3rd buffer as another way to bind information together from different types of sensory stimuli. And he talked about this episodic buffer as being multimodal. So it's not just limited to visual or auditory, but it can be any types of stimuli, and furthermore you can combine the stimuli from different types of modes: visual, tactile, verbal, etc. There's also the central executive, and the central executive, we talk about it as coordinating the components and integrating information from long-term memory storage. It plans, it regulates info, it inhibits or suppresses irrelevant information, and it seems to be particularly within the frontal lobe, because when people have damage to the frontal lobe, they seem to be poor at planning. But again, this idea that working memory is the information that's currently on your workbench that you're thinking about, that you're processing. And so you have these stores within the phonological loop, the visuospatial sketchpad, and episodic buffer, and you also have this active processing with the central executive, with planning and coordinating of information from these stores. And it's a good idea for us to talk about cognitive load at this point. When you think about working memory, you think about, there's only a certain number of things you can keep on your workbench. So if we're actually thinking about a workbench, you can think about it in terms of, well, there are only a certain number of tools that you could possibly have on there so that you can complete a task. You also need to consider, just what's going on in that learning environment, and something we think about as cognitive load. And cognitive load is the amount of mental resources required to complete a task. If you're interested in this line of research, Richard Mayer, that's Mayer, at the Department of Psychology at the University of California, Santa Barbara, has done a lot of research on cognitive load. And whenever he and his colleagues have talked about cognitive load, he talks about there are 3 different types. The first being intrinsic cognitive load. And this is just the load required to complete the task itself. So for example, if I give a student a passage to read, it will have a higher intrinsic cognitive load if there's a lot of left branching clauses in a sentence. So in other words, if the sentence structure is more complex, you're going to have a higher intrinsic cognitive load. But that's just the load required that is embedded in the task itself. Then there's this extraneous cognitive load. And this is the amount of mental resources needed to complete tasks irrelevant to the original task. For example, if you have, say, this passage to read, and then I give you some irrelevant material, so say, for example, I put a lot of irrelevant pictures on the screen, or I have redundancy where you're reading it, and then I also have verbal information in the background that doesn't quite correspond to the passage. This can lead to extraneous variables that will affect their learning. So resources are being usurped on things that aren't directly relevant to completing the task. Finally, there's germane cognitive load. And this is deep knowledge, including connecting information to old information and activation. When we think about germane cognitive load or germane processing, people sometimes refer to it as generative processing, and you engage in this deep processing, such as mentally organizing the material together, relating it to prior knowledge, such as schemas, and this can aid in learning. So we have intrinsic, which is, again, the cognitive load required in and of itself. Extraneous are things that are going to hurt, and germane seem to be ones that will facilitate. And the task demand will determine the cognitive load. So there's a lot of research being done, especially with thinking about so many classes being taught in an online domain with this idea of cognitive load. What is the best way for me to present this information to my student? What's going to lead to long-term retention? And again, there's a whole host of literature out there, and a lot of it's done by Mayer and colleagues. Ultimately, what we want to do is we want to transfer what we've been thinking about and working in memory to our long-term memory. And when we talk about long-term memory, we talk about it as being virtually unlimited in terms of capacity, and also being relatively permanent. And I say relatively permanent because oftentimes we'll talk about forgetting, and that may be because we might not have the right cues to access that particular target memory, or the links might be weak. But we have to first get it into long-term memory if we're going to retrieve it. So maybe you just didn't get it in there in the first place. Just how do you get information into long-term memory? 2 different ways, and that is through elaborative rehearsal and maintenance rehearsal. With elaborative rehearsal, this is a deeper way of getting the ideas into memory. And this is by keeping information in memory by connecting it to previously held memories. Think about it in terms of connecting it to your prior schemas, relating it to prior knowledge. Therefore, you are making a connection with the new with something with the old. So you're really having to think about, how does this fit with what I already know? And this is a deeper level of processing. Another way to do it is maintenance rehearsal. This is more shallow in terms of processing. And here what you do is you keep information in memory by repeating it to yourself, such as if I just gave you the telephone number 434-1492, okay, the way to retain it there would be 434-1492, 434-1492, 434-1492. Whereas if you were doing elaborative rehearsal, you might say 434 was this old area code where I used to live, So I'll think about 434 being connected to that area code, and 1492 related to a historical event. And so that's how you would remember that in terms of laboratory rehearsal versus just repeating it over and over again for maintenance rehearsal. And I was referring to shallow versus deep processing of information. And this relates to the level of processing theory. And this theory states that the amount of time information will remain in memory is directly related to the level of analysis and connection to other information. So if you are thinking more deeply about the information, then this should lead to better long-term retention of the information. Now, this is somewhat of a circular message in that deeper processing leads to better memory. Better memory could lead to better processing, but nonetheless, it seems to be the case that oftentimes we find that when you think more elaborately about something, oftentimes this does result in better memory. And we'll talk about a classic study by Craig and Tolving in 1975. And this was a study that showed, or one of the studies that showed, deep processing led to better memory. Now, in this study, they had participants in one of four conditions: in a structural, phonemic, category, or sentence condition. And these conditions varied on their degree of level of processing, with structural being the most shallow to sentence being the most deep. If you were in the structural condition, you would see a word for 200 milliseconds on the screen, and you would answer yes or no, is the word in capital letters. So if you saw table in the box, you would say yes if it's in all caps, and you would say no if only the first letter of the word was capitalized. For phonemic, you would be flashed with the word crate, and your decision would be, does the word rhyme with weight? And either yes, no. For category, you would decide, is the word a type of fish? So you'd be shown a number of different words, and you'd have to decide yes or no if it's a type of fish. And finally, with sentence, you would have, he met a blank in the street, and you would have to decide yes or no if that word fits that sentence. And we'll take a look at the results next. What Craig and Tolving found was that the best type of memory processing were the deeper level of processing, and that was the category and the sentence. And notice that just thinking about it in terms of structural terms, you really don't even think about the word that much itself. And so they suggested that deeper levels of processing led to better memory. Overall, what we're suggesting here is we want to make things that are connected to other items in memory. We want to think about it in an elaborate way. We want to think about it in a deeper way to make sure that it gets into long-term memory and that's more likely to be maintained. Now, we can also talk about the flip side of this in terms of not getting memory in, but instead you've gotten the memory in, but you seem to not be able to get it out. And that's with forgetting. And we'll talk about a couple of ways to forget. Now, when we talk about forgetting, oftentimes people will refer to decay. And we know that sensory information does decay, but whenever we're talking about memory from long-term memory, there's usually problems with this account. Decay simply means that information in memory is lost through time. And there was a study that looked at this with people who were given a task in which they had to recall a number of syllables. And they had a couple of conditions in this particular study. In the study by Jenkins and Dallenbach, 1924, another classic study, what they found was that when they trained people with nonsense syllables, they had them try to remember these nonsense syllables, and then participants either were able to sleep or stay awake after this training session with learning these nonsense syllables. Both groups were tested at equal intervals. But what you find if you look at this graph here is that those in the sleep condition were better because they didn't have interfering material. So it's not that it's through the passage of time that the stuff just decays, but it seems to be that with old classic theories of decay, that there was something that was interfering with it. Now, no one would suggest that through lack of use that things don't seem to drop off or become weaker, but what we find is that typically some of these decay effects from long-term memory are actually more readily explained by interference. And that is that information entering memory is interfered with. So you have a couple of scenarios here where think about it learning a new phone number. Now, when you've had an old phone number for years and you're trying to learn a new phone number, it's really difficult because the link between your representation of your old phone number is very strong. So if someone asks you what your phone number is, you might give them your old phone number just because that information is interfering. So there's a strong connection between that memory representation for your old phone number and a weaker one for your new number, so it interferes. You can have the flip, so that whenever you have someone ask you your old phone number, you might not be able to retrieve it very well, because now what happens is that new number is interfering with the retrieval of your old information. Another analogous example would be trying to remember where you used to live if you've changed addresses. Now, the reason why we don't say that this is really unlearning is because other studies have gone on, such as Melton and Irwin. They talk about when you give people a recognition test. So if I actually showed you your old number, you would recognize it. So it's not that you have some sort of unlearning occurring, it's just that memory is harder to retrieve because something is interfering with accessing it. Throughout this model, when we're talking about learning new information and retrieving this information, we've talked about how prior knowledge can aid in learning new information. So before we conclude this lecture, it's important for us to think about the different types of knowledge that we have. There's general knowledge, which just refers to the general cognitive abilities that we have, such as our ability to plan, to solve problems, to comprehend different information in our environment, which is contrasted to specific knowledge, such as I have a lot of specific knowledge about psychology, however, I don't have a lot of specific knowledge about biochemistry. So this can be subject specific. We can also talk about declarative knowledge, and that's whenever you can declare something. Think about it that way. This is verbal information such as facts, and knowing that something is the case is a way they talk about it. Whenever we give someone a recognition task or a free recall task, and we ask them questions, they are declaring particular knowledge that they have. So they're telling us particular facts, and they can tell us why that is the case. For example, if I ask you who was the 16th president, someone could say, I know that it was Abraham Lincoln. This is a fact. With procedural knowledge, this is knowledge that is demonstrated when we perform a task, and so we talk about it as knowing how. Procedural knowledge can include things like riding a bicycle, tying your shoes. If anyone ever tries to teach a kid how to tie his or her shoes, it's really difficult because we know how to do it, but it's not that we necessarily can be able to declare the processes behind it. And finally, there's self-regulatory knowledge, and this is knowing how to manage your learning or knowing when and how to use your procedural or declarative knowledge. And we'll talk more about this is more closely related to metacognition, and we'll be talking about metacognition in subsequent chapters. But we have these different forms of knowledge that, again, can aid in our learning of new information and also retrieving that information. Finally, we'll talk about two different types of memory. There's a distinction between explicit and implicit memories. Explicit memory is memory accompanied by an awareness of remembering. With semantic memory, these are memories for facts, such as, who was the 16th president, who was the first person to scale Mount Everest, and so forth. What is 2 plus 2? And we can contrast this to episodic memory, which is memory for episodes. You can think about memory for events, autobiographical memories, etc. But we have this sense of awareness that we are remembering something, which is in contrast to implicit memory, and this is not accompanied by awareness of remembering. There have been a lot of classic studies with people who oftentimes will have explicit memory failure, so if you ask them a question, they don't demonstrate learning, but implicitly they are showing learning. And your book talks about various ways that there is implicit learning with classical conditioning, procedural learning, which we talked a little bit about procedural knowledge on the previous slide, and priming effects, how if we prime someone, they're faster to respond. For example, we can prime someone with a negative stereotype. We talked about stereotype threat in a previous chapter. Well, if we prime them with a bunch of words that make them think that they're going to fail, this can actually affect their performance without them even being aware that you primed them of these particular items. Implicit memory, we can see that we can find that people are learning. For example, people who are unable to form new memories will show learning. There's a really mean characterization of a doctor who had a patient who could not learn new information, and one day he put a tack in his hand and he went to shake her hand, and the tack pricked her. Well, the very next day, when he went to extend his hand to shake her hand, she wouldn't do it. When they asked her why she wouldn't shake his hand, she couldn't say. But she remembered that association, even though she couldn't explicitly articulate it. And that is a way to capture the distinction between explicit memory, having this awareness of remembering, and implicit memory, and that's, again, memory not accompanied by this awareness.